In this lesson 7.6, we're going to look at a process called linear programming to help us solve a problem. Take a moment on your own to read through the problem below. You can pause the video and restart it when you're ready. The first thing we want to do in this process is assign our variables. We want to say what x and y represent. Let's let x represent the number of graphing calculators and y represent the number of scientific calculators. When assigning our variables, we want to think about what the problem is asking us to do. Usually in the very last sentence, it says how many of each type of calculators should be made to maximize profits. So we want our variables ultimately to represent the two different types of calculators. The next thing we'll do in this process is write out our constraints. Constraints are some limitations that we have in the problem. We'll always write constraints out as inequality statements. We'll look at this first phrase, at least 80 graphing calculators must be produced every day. If x is the number of graphing calculators, we can write this as an inequality. X must be greater than or equal to 80. Very similar, we also must produce at least 100 scientific calculators per day, so we could write y must be greater than or equal to 100. Last, it says that the team is allotted $510 to manufacture each type of calculator. We're going to need to use this information telling us about the cost. The cost to produce a graphing calculator is $225. So we'll do 225 times the number of graphing calculators, which is x, and the cost to produce a scientific calculator is $1.50. So we'll add on $1.50 times the number of scientific calculators, which is y, must be less than or equal to $510. Next, we're going to write out our objective function. The objective or goal is to maximize profit, and so the objective function in this problem is the profit function. We are going to write an equation to represent our profit. If we look at information given to us toward the end of the problem, it says that graphing calculators produced a $5 profit, scientific calculators produce a $2 profit. So if we let the letter P represent profit, $5 per graphing calculator plus $2 per scientific calculator. Next, we're going to graph and shade the constraint inequalities. We're going to graph them as if they were a system of inequalities. We could start by looking at those single variable inequalities. X must be greater than or equal to 80. We can start by plotting a point on the x-axis, labeling it with the amount. This is just a sketch, and so it does not have to be perfect. Remember, the x inequalities will be vertical lines, and then the x values that are greater than 80 are to the right. So we can think about the little shading arrows telling us ultimately where we would shade. All right, we also have an inequality telling us that the y variable, scientific calculators, must be greater than or equal to 100. So we'll plot a point here on the y-axis, label this as 100. This is going to show up as a horizontal line. And the y values that are greater than 100 are going to be above the line. So that's where the shading would be on that one. All right, for the last inequality, I'm going to actually rewrite mine over here on the side so I can see it. We could think about finding the x and the y-intercept, and so if we use the method we talked about in class on Tuesday, if we cover up the x, we could solve this part to find the y-intercept. So by doing 510 divided by 1.5, we get 340. Similarly, we could cover up the 1.5y and solve the equation 2.25x equals 510. If we divide both sides by 2.25, 510 divided by 2.25 is 226.7. That will be the x-intercept. We'll go ahead and draw a line connecting these two. Now, if we think about doing the test point of 0, 0, if we plug it in, we get 0 is less than 510, which is true. That means that we're going to shade toward the test point, which will appear to be below the line. And here we see we have a small triangle section in the middle where the shading overlaps. We're going to shade that in. Every single point inside of this shaded region represents an XY coordinate pair, where X is the number of graphing calculators, Y is the number of scientific calculators, and all of these combinations, these possibilities, they meet all of our constraints. And so moving forward, we're going to figure out which point in this shaded region will give us the maximum profit. It turns out that it will always be one of the corner points. It will never be a point that's randomly in the middle. And so we're going to continue by finding the XY coordinates of each of these corners. And we will call these vertex points. Vertex number 1, this one is easy to get. We can see that the X value is 80 and the Y value is 100. No work needs to be done to find that. All right, let's look at vertex number 2 right above. In order to find the coordinates of this point is really the intersection point between this diagonal line and this vertical line. Remember, earlier in Chapter 7, we talked about solving a system of equations to find the point of intersection. And so if we were to put the system together, our vertical line equation would be x equals 80. The diagonal line equation, it comes from the constraint inequality, but we're going to turn it into an equation. And this equation, or this system, will be very easy for us to solve. We can think about doing substitution. We know that the x value is 80, so all we have to do is plug in 80 for x into the second equation. All right, we can go ahead and subtract 180 from both sides, and divide both sides by 1.5 to get the y coordinate of 220. Altogether, the coordinates of our vertex, when x is 80, y is 220. Okay, we're going to follow a similar process to find our third vertex point over here. Like we did for the second vertex, we're going to put together a system of equations. This third vertex point is made by the intersecting lines, the horizontal line, which that equation is y equals 100, and the diagonal line, which is the same as we said before. All right, similar process as what we just did. We know that y is equal to 100, so we're going to plug 100 in for y into the bottom equation. We'll go ahead and subtract 150 from both sides to get 360, and then divide by 225, to get our x coordinate of 160. All right, so our final vertex point, the x coordinate is 160. We already know the y value up there is 100. Now, if you turn your paper over to the back side, we're going to move into our final step. We're going to take those same vertex points that we found and plug them into a table. So we had 80, 100, 80, 220, and 160, 100. Each vertex point represents a combination of graphing and scientific calculators that meet all of our constraints. So it could be 80 graphing calculators and 100 scientific calculators, and so on. We're going to see which combination will give us our maximum profit. So here's where we're going to use that objective function that we came up with at the start. At the top of my chart, I like to rewrite my equation so I know exactly where I'm plugging my numbers in, making sure that the x and y are lined up. For this first combination, we end up with a profit of $600. We'll plug our next point in. The next combination gives us a profit of $840. And plugging in our last combination, we end up with a profit of $1,000. All right, so we want to use this to determine which point maximizes our profit. It's going to be the last vertex point, which represents the combination 160 graphing calculators and 100 scientific calculators for a maximum profit of $1,000. So to summarize our steps for linear programming, we're going to start by assigning our variables. We wrote our constraint inequalities. We write the objective function. We want to graph the constraint inequalities, figure out where the shading overlaps, find each vertex or corner point of the region where the shading overlaps, which is also called the feasible region. We're going to plug the values of each vertex point to the objective function and identify which point maximizes the objective function. Sometimes linear programming is used to figure out something that can be minimized. Our two examples we're looking at today in class both have to do with maximizing. So these are the steps that I will be looking for. In the second problem that we do, you'll notice that there's not much of a template there. It's just a big open space, and that's really similar to what you'll see on the quiz and on the test. But these are all of the steps that I will be looking for that you will receive points for when you do these problems on your own. All right, so we're going to take a look at this last problem. Take a moment to read through the question on your own. You can pause the video if you need to and restart it when you're ready. All right, starting with our first step, we're going to assign our variables again, thinking about x and y. Looking at the last statement, the last part of the question is how many of each type of chair should be made in order to maximize profits. The two different types of chairs we have are rockers and swivels. So let's let x represent the number of rockers and y represent the number of swivels. Okay, thinking about our constraint inequalities, we want to think about some things that we are limited by in this problem. All right, so we have machine A and machine B. We have to work on both machines to make both chairs. And right here, it tells us some of our limitations. Machine A can run no more than 20 hours a day. Machine B is limited to 15 hours a day. So we're going to have a constraint for machine A. We'll have another constraint for machine B. All right, continuing on, the rocker requires 2 hours on machine A. So let's do 2 hours times the number of rockers. Moving forward, a swivel chair requires 4 hours on machine A. And we know that machine A can run no more than 20 hours per day. Now we're going to do a similar inequality statement for machine B. It says up here that a rocker requires 3 hours on machine B, so we'll do 3x. The swivel requires 1 hour on machine B, and B is limited to 15 hours per day. These are our only two constraints in this problem. Next, we'll think about setting up the objective function, which has to do with our goal, again, which is to maximize profit. So the objective function is really the profit function. It says that a rocker will make a profit of $12, 12x, while a swivel will make a profit of $10 plus 10y. Now we're going to think about graphing our system of constraints. When you have a big open space, just go ahead and draw in a basic L-shaped graph. It's really just a sketch of a graph. It does not have to be perfect or accurate. We can go ahead and label our axes X and Y. All right, let's think about graphing the machine A constraint. If we cover up the Y and solve for X, we get the X-intercept to be 10. If we cover up the 2x and solve for y, we get our y-intercept to be 5. So we'll go ahead and connect the x and the y-intercept. Thinking about our test point, if you plug in 0, 0, 0 is less than 20. That's true. So we're going to shade toward the test point. We'll just do our little arrows pointing down. All right, for our second line for machine B, if you cover up the x, we see the y-intercept is 15. Notice how my spacing is not perfect, but it's just a sketch as long as you plot the intercept, label the point, put the bigger number higher, of course. All right, and the x-intercept, we're going to think about covering up the y and solve for x, and so we'll divide both sides by 3, and we get the x-intercept to be 5. All right, we'll go ahead and connect these two. We're going to think again about doing the test point of 0, 0 to figure out the shading. 0 is less than 15. That one is also true. So we're going to shade toward the test point, which is below the line. All right, so we have this little section down here where our shading overlaps. There are actually 4 vertex points, 4 corners that are created. So I'm going to add some points in. And we'll go ahead and circle these 4 just to really highlight them. All right, now unlike the last problem, 3 of the vertex points are very easy to find. Actually, in the last problem, that first vertex was easy. We had to do a little bit of work to find the other 2. In this problem, we can easily get the first vertex down here, 0, 0. The next vertex is a y-intercept value, 0, 5. The next one down here is an x-intercept value, 5, 0. It doesn't always work out this way where it's the same number. In order to find our 4th vertex point, we will have to do a little bit of work. We will need to solve the system of equations for these 2 intersecting lines. So I'm going to show that work off to the side over here. The system of equations will be based on the boundary line equations coming from the constraint inequalities. All right, to solve the system, you could do substitution easily by solving for y in the bottom equation, or you could do the elimination method. I might just do elimination by multiplying everything in the second equation by -4. That way we could eliminate the y variable. So that would give me -12x minus 4y equals -60. I'm going to go ahead and highlight now the 2 equations that I'm adding together, the top equation and the new version of the second equation. When we put the x's together, we get -10x. The y's are going to cancel. On the other side, it's equal to -40. Divide both sides by -10, we get x equals 4. Now we'll want to plug it back into either one of the original equations. I'm just going to plug it into the second equation. So we have 3 times 4 plus y equals 15. So we end up getting y equals 3. So these are the x and y coordinates of that last vertex point, the point of intersection between those 2 boundary lines, 4, 3. Okay, now our final step, we get to plug these vertex point values into our profit equation to see which one will give us our maximum profit. So if we have 0 rockers and 0 swivels, it makes sense that we're not going to make much money. We get $0 for that profit. When we plug in the next possibility, I forget which one is which. The next possibility is 0 rockers and 5 swivels. Okay, so that will give us a profit of $50. The third possibility is 5 rockers and 0 swivels. This one is a little bit better. That gives us a profit of $60. And then the last combination is a combination of 4 rockers and 3 swivels. And that will give us a profit of $78. And so that one is the most. We can go ahead and circle the vertex point, circle the profit. And then when we're writing out our solution, let's write out in words how many of each type are needed to maximize profit. So we can write out that it will be 4 rockers and 3 swivels for a maximum profit of $78.